Hi everyone, and welcome to Mr. Carlson's lab. This is episode 3 of the Vedolyzer. It's been a very long restoration and rebuild process, so let's bring this thing back to life and make it work. In the last video, we left off at the point to where I had to change out all the capacitors aside from this assembly in the center, which was rebuilt in an earlier video. So there's still a lot of wax capacitors all over the place. There's electrolytics here that have to be changed, one here, and there's also a bunch of filter capacitors inside this paper block here. There's 2 of them in here. What I'm going to try and do with the filter caps is I'm going to try and get them as close to the rectifier on the bottom portion of the chassis as possible, and that'll free up a lot of room in this area here for me to work. Not only that, I'd like to get all the work in this area completed before I move on to anything else. Reason being is the wires on all of these coils for the wave meter is very, very fragile, and if I bump them or hit them with anything, I don't want to damage any of these coils, because that just adds more time to this rebuild. So I'll get this whole section here done, and I'll most likely relocate most of the filters into this area here, right by this filter choke over here, and then I can just move on to the other sections. So I'll get the electrolytics done first, and then I'll start changing out all the rest of the waxies. Now, there has been some intentional damage done to this thing, and I'm going to go over that here in just a little bit. I guess some tech way back when figured that he'd make servicing easier, and he intentionally damaged some parts that are irreplaceable. So I'm going to have to go through and somehow either make something or modify the unit so that that one particular section will work. Again, when I get to that point, I'll show you what he's done. It's pretty bad. And then I'll go about addressing that fault when I get there. So one problem at a time. There's also a bunch of capacitors on the back side here, right where the CRT plugs in. So those all have to be changed as well. So lots and lots of stuff. So I'll end up going over the actual schematic for this model here in a bit. So Don at Restore Old Radios, that's his YouTube channel, was nice enough to hunt this schematic down. This was unobtainium. I could not find this anywhere. He found this schematic and gave me a link to it, and I was extremely surprised this piece of paper is for this model. So since then, I notified Steven Johnson, and he has the Supreme site, and I gave him the link to this schematic here. So now he has this schematic on his site as well. So definitely check out Don at Restore Old Radios if you're into this kind of stuff. Check his site out. He does a lot of radio restorations and a lot of really good work. So I'll put his link just below this video under the description, under the Show More tab. So just below the video description, you'll see a Show More in capitals. Just click on that and I'll have his link there, and also link in Steven Johnson's site as well. He has all the information on this. He has instructions and more generic information on the Vedolyzer on actually both models that were put out. It seems like this was a model and then there was another model with lesser tubes in it. So he'll have all the information there if you want to follow along with schematics and alignment procedure and things like that. So both Steven Johnson and Don at Restore Old Radios will be under the Show More tab. Definitely check them out. And if you're interested in restoring old radios, definitely subscribe to Don's channel as well. It's a really good channel. So I'm back into this thing here again. I'm going to get rid of all of these caps, and hopefully after that, maybe I can patch in a line cord. I can pop the CRT in the front and we can see if at least the CRT glows, which would be a really nice thing. And if, the B plus is available and all that kind of stuff. And at that point, that's a lot more motivation to keep on going and work harder to get this thing going faster. This thing has been just an absolute incredible amount of work cleaning the chassis alone, removing all the parts and pieces that have already been put on and putting them all back in, and learning some of the mistakes that Supreme made as well. One was a drilling error with this switch right here. The switch is, if you notice, it's in kind of crooked. So looks like they off-drilled the hole here. It should have been down. Either that or, they've used a different shield on here because the switch was just mounted in there crooked. There's no other way around it. It's just the way it goes in. So there's a few little interesting things that I've noticed along the way, but it is coming along, and hopefully very soon this thing will be to life. And through the magic of the camera, days worth of work turns into mere seconds. So I've replaced all the electrolytic capacitors and all the paper and foil type capacitors. That's one question I get all the time. People say, don't you mean paper in oil? No, I mean paper and foil type capacitors. So those have all been replaced. I've replaced all the electrolytics here. So that block that you saw here, which is in this box of parts, I'll just grab this. This is some of the parts that have been replaced out of this so far. Still more are going to be added because I still have to replace more components, but this is just some of them. And you really don't get an idea of the depth of the box and all the components in here. Lots and lots of stuff. So this capacitor right here. So this one right here. Let's get this out of the way. Was right here. And that has been replaced with this. There's a capacitor here, a capacitor down here, and there's another capacitor over there. So there's two capacitors in that block, which are in the power supply here. So there's two capacitors within that block. Now, the way they had this wired up, it was a combination of basically one on this line and one over here, and then there was another separate capacitor. So somebody's been in here over time and they've been replacing caps. So I don't know if they've moved things around. Maybe at one time there was a capacitor that had failed and they needed to patch it, so they moved one into another area. I really don't know, because this thing is just, over time, it's been so badly butchered, right? Somebody was in here and they've done horrible things to this, and I'll show you some of those horrible things that they've done here in a little bit. This is all part of the restoration time. Now, this is part 3 of this video, and what I'm doing here is I'm just going to give you the highlights of what's been done. If I was to take you through the entire procedure of me putting these in and going through and finding all of these little parts and pieces, this video would end up being another 3-hour video. So again, what I'm trying to do here is just focus on all the highlighted stuff. I know some of you like the really, really long videos, and some of you don't, so I'm trying to find that nice little balance point here, so that I'm not showing you every part and piece that I'm testing and replacing and things like that in this, because this has been such a crazy project, right? To date, on YouTube, so you're looking at the date of this video here, this is the most in-depth restoration that I've ever taken on. This thing has had the most wrong with it. It's been the most butchered up. This has just been an absolute handful, right down to the point. I don't know if I explained this in a previous video, because it's been quite a bit of time since that last video, but I've had like this entire thing when the vertical amplifier was out of here. So this was rebuilt in a video, this whole section here, and it was put back in. When this was out and a lot of the parts and pieces and components were out and the face was off of this, I took this thing outside, sprayed the entire chassis down with simple green, and hosed it off with a hose. It was in such bad condition. It was just absolutely, it was just filthy, and you couldn't get in all the little parts and pieces and nooks and crannies. And of course, before I did that, I sprayed down all the potentiometers and VRs and everything with WD-40 before I did that process. After I did that process, I air dried the whole thing off with a compressor. So I blew all the air out, put the thing in the hot sun for a day. This thing was cooking hot. It dried out right now. And while it was doing that, I sprayed the thing down with WD-40 again. And I mean, this thing was soaking. It was dripping. I could almost pour WD-40 out of this thing. And that way, nothing is going to rust, none of the VRs will get hurt, none of the contacts. And if WD-40 sits on these things for a long period of time, it actually works as a cleaner. So it worked out very, very well. I've tested the switches and the VRs for continuity. I'll talk about a set here that is a real pain. Somebody really butchered that up. But I've tested everything for continuity, and it's all working very, very well. Now, this is very common practice when you're dealing with something like this. You mask off things like this or remove them or cover up the power transformer, things like that. You can hose down a power transformer, of course, the unit being unplugged. You can hose down a power transformer as you're cleaning the thing off, as long as there's a very long time for it to sit so that it dries out. These older power transformers are, coated in wax. You hose the thing down, and if it... this thing here sat for, about a week and a half, and it was out in the sun repeatedly, it's going to completely dry out. And this is actually pretty common practice for cleaning a lot of this older stuff out, and it works just fine, as you see. Now, the chassis on this thing was so incredibly pitted to begin with. I polished it up the best that I can. On the bottom, it doesn't look so bad. On the top, it is really pitted. Now, the thing's going to be sitting in a cabinet. I'm not going to be staring at the chassis all the time. It still looks pretty good, but it is a little rough. So instead of me stripping the entire chassis out, having this thing replated and putting all back in, that would add an entirely different level to working on this thing. A lot of these wires in here are so incredibly brittle. You move anything around and they'll come off of the terminal just because they've been moved throughout time by other technicians to get them out of the way. And this schematic that Don had sent me the link to is absolutely wonderful. This really helped out with this. This is so incredibly different than the original Vedolyzer schematic. And the values that were replaced in this vertical amplifier before I had this, so I reverse engineered this entire vertical amplifier before I worked on it because I didn't have the actual schematic for it. And thankfully, the person that had replaced the components in here previous to me, because I reverse engineered this to the components that they had. And then if some of them didn't make sense, I would go in there and correct them to where they made sense. It came out extremely close to the schematic. So incredibly close. And, the values are, I would say so acceptable that I didn't even have to do anything to it. It's still the same thing. I've changed absolutely nothing in here since I reverse engineered it, and I've looked at this thing here. So that worked out really nice because I really didn't want to go back in here and start tinkering around with this again, because this was an incredible amount of work, as seen in the earlier videos here. So the chassis is nice and clean. I haven't put any of these tubes back in. The tubes are in the vertical amplifier. They're stuck in there, but I haven't stuck any of the other tubes back in yet. I still have to clean them up, and I haven't tested the CRT. I think I'll just use this device to test the CRT. Now, I'm hoping that the CRT is okay. So it's a 906, as you can see here. If it's not okay, I'll have to source another one. I might have another one or two hiding somewhere deep in area number 3. I'm not sure. But if this one's working, I really hope it is, then I can just use that. The power transformer, I've gone through so much work on this chassis now by replacing all the parts and pieces in here that if the power transformer or, the filter choke is bad, I'll just end up either rewinding it or I'll go through my stash of power transformers and find another one that'll work. It's not really too incredibly specialized. A lot of oscilloscope power transformers of these years is set up the exact same way. They've got separate filament windings and there's multiple taps on the rectifier windings, and then of course we've got one rectifier that's normal and the other one that's reversed to create a negative supply, and then we're dealing with a kilovolt here, so it's 1000 volts AC in this chassis, and it sources a lot of current. So always something to keep in mind when you're working on vacuum tube gear. Lots of voltage, and this transformer is big enough that that could very easily be fatal if you came across it. Never ever forget that when you're working on anything vacuum tube. I can never stress that enough. So this takes that AC and changes it into direct current, but it's negative. And what ends up happening is we go through our, bunch of resistors here. Is the intensity and focus stack and everything in here. So now when I went through this and put this thing all back together, because I had the face off of this and I had all of these switches and everything out, and of course, as I mentioned earlier, everything's hosed down with WD-40 and it sat for a long period of time. And then I did it again, with exceptions of, this and, some of the coils and things like that. And everything turned out really, really well. All the switches are making great contact, as I mentioned earlier. And I wanted to make sure before I put this entire thing back together that, putting the face on it and putting all the switches, bolting all the switches up to it and VRs and everything, that everything was working okay. So I went through and I tested the variable resistors, all the VRs on the face, and they all seemed to be okay. With the exception of this hack job right here. Now, this is what I'm talking about by that previous tech, and if any of you recognize this right here, you're probably going, oh man, yes, somebody drilled holes in the cases of these VRs. So, what I did is I measured from end to end on the variable resistor. Now, this is a very specialized variable resistor. This isn't something that you're going to come across every day. You either have to do something solid state with a bunch of pass elements to replace this, or you would have to order something up custom. So if we take a quick look at the schematic here, I'll just zoom on into this so we can get a little closer. So we take a quicker look at the schematic. You can see that this is one of the vertical sensitivity, so vertical gain 1. There's a 450 ohm VR here. And this is gang to number 2, which is over here, which is 5M. So that means that it's 5K. It's another thing that's very confusing about these schematics. I'll go over that in a moment. I've explained this in other videos, but I'll just briefly touch on it, on that thing here in just a moment. So very specialized. These are hooked together. So we have a 450 ohm and a 5K VR hooked together, and you know they're going to be able to deal with a substantial amount of current. Now, the reason that there might be holes drilled in here by some hack in the past. Now, here's another thing. Whenever you hear me say the word hack, it's not like the modern day hacker. So hack used to mean if you were a hack and you worked on something, you're a butcher. All right, that's how it was. So nowadays, you know, you've got makers and hackers, and that's a completely different meaning. So I often say the word hack, and I think it comes across wrong because of this. So when I say hack, I mean butcher, okay? So some earlier hack was in here and drilled those holes. And what ends up happening when you drill holes, I'll just get this out of here so I can get the exposure up a bit. What happens when you drill holes like this in a case is it's very hard to keep that metal out of the inside of the VR. Now, chances are he did this so he wouldn't have to remove the VR. The sides of the VR are tight on the actual case, which means that the cap wasn't removed when he did this, or she, or whoever did this. Drilled the holes in. So it's very difficult to keep, when you're drilling a hole in something like this, a little piece of metal from falling in there. And all it takes is one little piece to fall inside and it can completely destroy this. And of course, if there's high voltage on this VR, you know, it'll arc out inside and create smoke and do all sorts of bad things. So looking at this, I'm going, great, I know what's happening here, right? So what I did is I took my ohm meter and put it across. Now, thankfully, this still measures close to 5K, and the front one measures close to about 500 ohms, actually. Here's where the problem lies. When I move the VR around, the wiper that's rubbing along the track inside is going, it sees resistance and then it goes missing, and it sees resistance and it goes missing, and it goes up into the megs, and then it comes back down. So the actual track inside is really dirty. Now that could be because of a bunch of things. You know, the dirt may have gotten inside this thing through those holes and caused the actual track to get dirty. Or it, you know, might be that the actual wipers are damaged from him drilling holes. I really don't know at this point. So what I'm going to do is I'm going to do the same thing that he did. I'm going to put a pipe in here, and I'm going to blast some of my favorite contact cleaner inside this, move it around, I don't know, 20, 30, 40 times, back and forth from stop to stop, hose it down again in each hole, and do the same thing over and over and over again with a rag under here to soak it all up. Basically, I want a puddle laying in here so the chassis will be up on its side. I want a puddle laying in here so that wiper's going to dip in it. And then, you know, basically, you know, swish it around on the carbon track, and I'll see if it comes back to life. If it does, it does. If it doesn't, that opens up an entire different part of this restoration. So again, just absolutely unobtainium, right? Now, this looks like a really strange thing here. You know, there's which is a 40K resistor, so 4 0 and then 3 zeros, so yellow, black, and orange. There's a 40K resistor tying right to the input to where the vertical sensitivity comes in, and that's for all three of the inputs. It goes through a VR to ground. Now, the only reason that this thing is here is to create some form of gain correction when they have the graticule on the face of the CRT. The graticule for this thing is long gone, and finding any type of accuracy to their divisions is kind of crazy anyways with a device like this. So when I rebuilt the vertical amplifier, I had a lot of people say, well, have you tested to see how flat it is? And I just laugh. This thing is built in 1939. Flat? What is flat? Square wave? What is a square wave? Fast rising and falling edges? Yeah, good luck with that. So at any rate, this is in the years when you're using this thing to, align basically early televisions, and you're using this to look at sine waves and things like that. So I can tell you this right now, that in no way, shape, or form is this vertical amplifier going to be anywhere near flat. And even if they did get it close to flat, it would be very interesting to see what they used to try and get that flat back in these days. So the reticule on the face would have been accurate to a degree, but, it would have been, not incredibly accurate at all. And any of you test equipment buffs out there that, think that this would be any more accurate than what I'm stating, just look into the specs of these things. They're all over the place. So I'm not too worried about the reticule. We don't need the reticule for what we're going to be doing with this thing anyways. So what we're going to be doing with this thing in the future is, servicing modern equipment. I want to service switch mode power supplies with this, and, radios and test equipment and all sorts of things with this. And the whole goal of this is to show all of you how to repair modern devices with older gear, because this older gear is still very valuable. All it takes is a combination of two things: your gray matter and the device itself. So nowadays, with the modern test equipment, it relies more on the device than your gray matter. This thing here still exercises your mind and makes you use your mind. And, once that's understood with using equipment like this, you wouldn't believe how easy it is to service modern equipment with a device from 1939. In fact, I like the challenge. It's fun. So we're going to do all of that kind of stuff here. So all of those old oscilloscopes and things that you find at ham radio swap meets and online auctions for $10, $15, $20, you can use to service modern gear. That's one of my goals, to show you how to do that, because it is quite easy. And it's actually a lot of fun, taking an older piece of equipment like this and giving it a purpose again. So test equipment is test equipment. So now I'll just zoom on into this here again. Now I'm going to explain what they've done with the resistors here. This is a really interesting thing that they did way back when, and this confuses a lot of techs nowadays, and I can completely understand why. So hopefully this isn't too dark. There's a lot of light shining on this thing, so my exposure is going down quite a bit. So you're going to see here, you can see that they've rated these VRs, right? 5M, 45M, it says for this fixed resistor here, 1M. Well, that means 5K, 45K, 1K in modern values. 7500 would be 7500 ohms, or 7.5K. When they want you to convert that to meg, they actually write meg after it, like 4 meg. So the difference between 25M and 4 meg is a world apart. 25M is 25K at 2 watts. It says here -2W. So hopefully you can see this okay. I'll zoom right on in. You see that? So that means 25K, 2 watts, 10K, 2 watts, 25K, 1 watt. Right? When you see something like this, when it says meg, it's meg. 5 meg, 1 meg. So that's something you need to keep in mind, and this traps a lot of the new techs that like to work on this kind of stuff. What is that? 2K. 200 ohms, 20 ohms, 40 ohms, 400 ohms, what's that? 4K ohms. This variable resistor is 20K. That is 40K. Now this is this horrible looking thing that they've tacked on to the backside here of this VR. So this thing here. Now I was talking about this a few moments ago. So this just looks like gain compensation again. So what they're doing here is they're trying to compensate the input gain, maybe limiting it off a little bit. Judging by the circuitry here without even trying this out, and then of course powering this thing up in the beginning, there is an incredible amount of gain in this section. So much so, I'll just zoom back in here again. As mentioned earlier, there's so much gain in this section here that they're actually taking the output of this 1852. They're putting this through a 0.0014 microfarad capacitor, and then they're shunting the output through a 2200 ohm resistor to ground. So they're taking that gain and just dumping it off at this point. Right? And that's before it goes through the circuitry here and comes back into the grid of this tube and then gets amplified again and amplified again. So this here is the driver basically for this thing here. But all these stages are going to act as a form of amplification, and they've spent some time in tuning and things like that as well. So I would say like this is just crazy gain in this section here. So they, as they say, they're dumping it to ground. So what they're probably trying to do is some form of compensation for the 3 input jacks here is dump that to ground. So, the maximum resistance here to ground would be about 60k ohms. So the input, it would see that if you fed something directly into that, you'd, have a 60k ohm load on the input here. Now, I imagine there's probably, it says here at the bottom, there's most likely going to be, in the red probe. So as you can see, it contains a 3 meg resistor and a 5 picofarad capacitor. Another trap, 5 mmFD means 5 picofarad in today's speak. Microfarad is picofarad. It says your blue probe, the IF probe, contains a 1.5 picofarad capacitor. It's like almost an open connection. So that's how much gain this thing has. So when you look at most radio IF sections, they have a lot of amplitude. So this is to basically allow you to look at the IF section in radios without overloading the crap out of this thing, right? The black probe AF contains a 0.37 meg. That looks like a decimal place. I think that's a decimal place. Good possibility. I can't see it being 37 megs. So 0.37 megs, that would be 370k ohm resistor down here. So different probes for different purposes. So I'll end up having to put some probes together for this, or just work on one universal one with a switch or something like that. There are the 3 jacks up at the front of this unit. So one for RF, one for IF, and one for AF. So RF stands for radio frequency, IF stands for intermediate frequency, and this is AVC, so automatic voltage control, and AF means audio frequency. So they just want you to attach the different probes and use the different probes, I guess, to keep this thing as working to the peak as possible. So you select the right probe for the right job, and there's a lot less thinking with all the controls on the face is basically what they're trying to tell you to do. If you use your gray matter a little bit, one probe would work for all, and you would just change the coupling. You could add a resistor in line with it or something like that. What else can I tell you about this? There is so much that has happened between the last videos. It's really hard to keep up. This thing has just been so incredibly in depth. Let's see, scanning over this, let me see. All of the original glue that they've put on these coils and all the capacitors look original, so I don't think anything has been moved. So it'll be interesting to see what the alignment is like in the wave meter, if the wave meter even works. These are adjustments for the VTVM section. So these are unlisted. They're in here. A little bit of tracing would indicate what these things are. So obviously calibration. Let's see. What else? Just lots of resistors changed. The resistors over here were changed. And there's a divider over here. That's 24K that actually I just talked about. So right here, this resistor, and this one was okay. So this 25K resistor was replaced with 24K, which is close enough. This 10K was like 20K. It was double its value. That had to go. So these were changed over here. And again, when I'm changing the capacitors, I don't want to go back in here and, desolder things to, change a resistor once I've put a new cap to the same terminal. That's the reason I've done this. So lots of things have happened within this chassis. They've done a bunch of things that make this very hard to clean up and make it look pretty. What they've done is they've taken wires and run them through the bottom of these terminal tie points, run them through the hole, and then they wrap them around the post. So even though you unsolder or desolder components in here, you still have that big mess wrapped around the post, so you have to kind of fit the new component over that wire wrap. So it is pretty ugly. Now that could all be cleaned up by taking all of these, terminal tie strips out of here and, clipping them off and then just soldering them in the bottom hole and putting on all the parts and pieces. Again, just adds another level to this restoration yet again, so I'm not going to end up doing that. Just, it's not worth it we're not looking at the underside of the chassis, put it that way. We're looking at the face when we're servicing things with this thing. So the whole idea is to make this thing dependable, and it's not going to be a shelf queen. This is going to be in regular service. So I just want this thing to work properly for a very long period of time. And I think with the components that have been replaced and the things that I've measured in here, I think I'm good for the long run, at least down here at any rate. Now, there's still components on the upper side that need to get replaced. So I'll talk about this here first. So this is the bias battery for the bottom side. So the amplifiers here, the vertical amplifier section, needs a negative bias on the control grid. And these batteries here supply that bias, gives about 3 volts, a little over 3 volts to the control grid of these vacuum tubes here. Now, without these batteries, if the batteries go dead, the tubes will draw heavy current because they're basically turning on without these batteries bringing them to a negative voltage. In modern equipment, they don't use batteries. What they end up doing is they'll take a tap off of the transformer and get some negative bias from there and run it over here, which they've done. They've created a negative bias section. Why they're not using it for the tubes at this point, I don't know. Most likely because batteries are very stable. If the bias moves around a little bit, the gain will move around as well. So by changing the bias, you're turning the tube on and off, you're changing the amount of current the tube is going to draw, and everything is going to change. And of course, the trace on the CRT will bob up and down with line voltage excursions, things like that, right? So the chances are that's the reason they did this, just to make it a little bit more stable. Now, there's 2 sets of batteries in this. There's these ones here. Now, this sits down in here like so. I can get this down in here. Like that. This sits in here like that, and then this screws up to the side to keep that in there. And then this, so the negative side of the battery ties down to this little binding post right down here, as I talked about in the earlier video when I rebuilt this, ties to this binding post. And the positive side of the battery solders to the chassis. Again, we need a negative voltage to shut the tubes off. Vacuum tubes are very much like FETs. They're voltage controlled devices. They're not a current controlled device like a transistor. Okay, like a normal, bipolar NPN type transistor. They require current to make them work, whereas FETs and vacuum tubes, they're, voltage controlled devices. Now, again, if I zoom on in to the schematic here just a little bit, there's a bunch of batteries in here that need to be replaced. These ones are on the upper side of the chassis. These are 2 D cells, soldered in series to make 3 volts. And then on the bottom portion of the chassis, we have the bias batteries, and the bias batteries are right here. So this here is what we just looked at, right here. So these need to be replaced. Now, here's the thing. Control grids of vacuum tubes, like the gate of FETs, are extremely high impedance, and there's virtually no current draw at all. Okay, so there's the batteries. These batteries actually still may be good. They might actually be fine still. So I'm going to measure them here in just a little bit just for the fun of it, but I'm going to replace them because we're in a restoration, and if I put another set of batteries in there, they should last another, who knows, 40 years, I hope, if they don't leak. So what was really neat is I went out looking for batteries that would be kind of, that would fit this, and I managed to find these, which are really neat. So they have the old number 9 with a cat jumping through it and a lightning tail happening on it, so that'll look kind of neat on the underside. Again, not too important because nobody's going to be looking in the underside of the chassis, but it was just neat to find something that kind of looks era-specific in this thing. So these are C cells. These will go over here, and then the D cells will go on the upper portion of the chassis, which I'll focus on here in just a little bit. So I'll get rid of those bias batteries. That's the next thing that I need to do on the bottom side. And of course, look at this VR up here and cycle it and make sure that it's okay. So I noticed this here right in the end. This was not long. I've been looking at this thing going, who butchered this thing in here? And what kind of a hack put that thing in there, right? So I was looking at this just going, man, soldered this to this. Why did they do that? And then I'm looking at the schematic. I'm going, oh, that was factory? So anyways, that must have been I'm sure this was an add-on in the end. They would have probably mounted this somewhere or they were at a chassis space. It's always interesting to see, as they're going through, the designers and, the little things that they've encountered down the road. Like this, the crooked wafer switch. So this thing in no way, shape, or form goes into the chassis straight. It's like this when it's screwed onto the chassis here. So you can actually almost see the angle here. There's just no way around it. That's the way the thing was put together. So the little things that you see in production, like nobody would have ever noticed that way back in the day, just because this thing probably never came apart, because when it was made, it was probably very dependable for a number of years. I've installed a brand new line cord at this point. I put the line cord in and some shielding over this. when I was working on this section here, because I don't want to go in this again. I don't want to tamper anything in this area because there's those fine wires under here. So I put the line cord in. Oddly enough, the rubber grommet that's on the back of the chassis is soft. So I tried to chip the rubber grommet off and it just squishes like a new rubber grommet. I'm like, wow, I guess I can just leave that. So I left that rubber grommet in, put the new line cord in with some of that high-heeled shielding over it, and then it's clamped to the chassis as a restraint, and then that runs to the top side of the chassis to the power transformer, and then one of the leads goes right to this little area right here. Now, to modern day safety specs, this is all shielded, and triple layers of heat shrink tubing on this, and then this would be covered by 15 layers of plastic, and there'd be an emergency number in here, and there'd be all sorts of kind of things for nowadays. Back in the day, they didn't do that kind of stuff because if you went in something like this, you just knew what you were up against, and if you didn't, you found out very fast. So again, this chassis here is a kilovolt or so in it. You can see here's 1,000 volts right at this point here, and that is direct current. That's out of this rectifier, negative. So the chassis is actually positive 1,000 volts to this point right here. And I'll get into why you don't get shocks off this kind of stuff. It all has to do with isolation and transformers. But at any rate, it's a negative 1,000 volt supply that's running to the CRT to make it do what it does. So lots of voltage, and this transformer in this thing is a monster. So that would source quite a bit of current. Always things to keep in mind when you're working in things like this. I can never stress that enough. All this old vacuum tube gear is, if you don't know what you're doing, it's extremely dangerous to work on. So don't do it unless you know what you're doing. And if you do, be very, very careful, because everywhere in this chassis is high voltage at some level. There's a 350 to 450 volt supply in here when the thing is loaded all the time, and there is an incredible amount of current there. Not only that, you have capacitors that are storing a charge. So these capacitors here can supply a lot of current, especially because there's so many of them on the same line. So, if I was to short that out with a jumper clip, it would blow the end of a jumper clip off. That's how much current there is supplied in the 400 volt area of this. So all the caps are rated at 450 volts in this thing. That's what they were. That's everything that was in here was rated at 450, even that little block that was sitting here. So that was just all replaced with, really high quality, high hour 450 volt capacitors, low ESR, high ripple current type capacitors. So again, when this is done, I don't want to go in here again. I want this done. I want to use this on the bench, and if I ever want to see what this looks like inside, I'll watch this video. So that's where I'm at on the underside of the chassis. So the next step for me, again, is to change these batteries. I'll put this in here. I'll see if I can get this VR working. If I can, I'll put this all back together. And then the next step really is to put power to this thing and see if the thing even works. Looking at the top side of the chassis, the next two batteries that I have to replace are these two D cells right here for the VTVM circuit. Everything else on the top of the chassis is pretty much finished. I left the factory high voltage capacitor in just because it tests so incredibly good on my leakage tester. No problems with this thing at all. So you can see on the top side of the capacitor there's two bolts, and that's where the high voltage is located, and that's how much of this old equipment was. So there's 1,000 volts present right there on the top side of the chassis, something to keep in mind if you're ever working on an older piece of equipment like this. Well, I can comfortably say the underside of the chassis is finished at this point. Now, when I go about testing this to see if it works, if some component shows up as being bad, one of the ones that's left over, something like that, I'll address that at that point. But this is pretty much done at this point. And that's a really nice thing. The new bias batteries are installed. The clamp that holds the batteries to the chassis here is really sharp, and it has a tendency to cut through the jacket on these newer type batteries. So what I did is I put some high heat shielded pipe. So this is a fibrous pipe, this kind of stuff that you find in toasters, over the clamp to act as a cushion to hold the batteries against here. So that way the clamp doesn't cut through the case of both of these batteries and make connection. That wouldn't be a good thing. I sprayed some contact cleaner in both of these VRs and worked that VR for a long time from stop to stop, and then hosed it down again, and then hosed it down again. And thankfully, the wiper in both of these VRs is now making connection again. And the actual movement of the VR is really smooth because I used so much of that contact cleaner in there. It worked out really, really well. So thankfully, I didn't have to take this out and work on a replacement, or even maybe hide some solid state stuff in here to, take place of both of these VRs. So hopefully it stays like that. It seems pretty solid and the connection is really solid. So I'm happy with that. On the upper portion of the chassis, I also changed out the other two batteries and put them in. So at this point, I'm pretty much ready to put the vacuum tubes in and turn the thing on. So what do you think? Is the thing going to work? That's a whole lot of wires that have been moved around in here. Well, let's find out. All right, the moment of truth is just about here. All I need to do now is put the CRT back in. The two index pins, which are the two larger pins, are right here. So this is pin 1, and it counts around like this, and the index is on the side, so it's on this side right here. So what I need to do is carefully place the CRT in here, and hopefully it will line up. There it is. It's in place. So let's see if the thing is going to fire up. So I guess fire wouldn't be the optimum word to be using right now. So I'll turn on my current limited isolation transformer and variac supply. And I have this down at about 35 volts. I'll turn the unit on. And we should see some very dim lighting happening. And it's not drawing any excessive current, so what I'm going to do is bump that up to about 75. You can see the little dial light come on, and you can see the filaments in the rectifier tubes over here coming on. You can see the little filament down there coming on. And it's not pulling excessive current, so this is a good thing. So I don't have any B+ monitoring or anything going on. I'm just watching the power supply over here, the current limited isolation transformer and variac supply. So I'm going to turn this right up. And it's all looking good so far. I don't see any light on the CRT. So what I'll do is I'll turn the intensity right up to the max. That's always a good thing. And I'll get the focus up to just about the top. And I'll move well, actually, let's get a sweep happening here. So I'll put this on, say that one there. If there's going to be a sweep, I'll move this around. Ah, look at that. There it is. It's alive. Well, that's a really good sign, and the CRT is nice and bright. It's really bright in the camera. So I can turn the intensity down here. And since it's so bright, it's actually looking brighter in the camera than it actually is. Well, this is looking really good. And the meter, which you can't see on the other side, is moving just a little bit. And it is moving with the 0, so this is all looking really good. So what I'm going to do now is there's a little cardboard shield that goes in here to stop the light from this dial from shining onto the back of the screen. I'm going to put all of that in here, and I'll put the bezel back on the CRT, and then I'll focus the camera on the face, and we'll go through a couple of the actual functions of this and see if it's working. So that'll be next. The Vedolyzer has been warming up for about 15 minutes now, so let's try out the VTVM portion here. So nothing has been done to this, no alignment, no anything. All I've done is just replaced all those components. I imagine this is going to take quite the alignment procedure. Lots of alignment points in this. So I'll plug in a probe here to the VTVM, positive and negative. The VTVM is off right now. So what I want to do is zero this. So it says 0 the volt scale. So what I'll do is I'll 0 that right there. And I'm going to put this onto the 2 volt DC position. So there's 1 volt right in the middle and 2 volts over here. And I'll test this battery right here. So it's about 1.6 and a bit volts. It's a brand new battery. So I'll just put this here and here. And look at that. It's testing just about 1.7 volts. So it's very, very close. That's actually really surprising. So no problems with that on the 2 volt scale there. What I should do is grab another battery. What I'll do is I'll go grab a 9 volt battery. And I'll see. I'm not sure what this is. I think these are down just a little bit. So it should be just a little lower than 9 volts. So I'll move this here to the 20 volt DC position. So that would be 20 volts, that would be 10 volts, that would be 9, and then 8 and 7 and so on. So I'll just test this out now. Actually, it's a little over 9 volts. That's just below 10. So what I'll do is I will grab my other meter that's off to the side and I'll check it out. I'll see if it is over 9 volts. So many probes and stuff all over the place here. Is it over 9 volts? It is. It's 9.1 volts. So I'll just pinch this here and put that there. You see that's 9.1 volts. So again, we'll take a look at it on the Vedolyzer. And yeah, it's just a little over 9 volts. So 2 scales are correct. So I'm imagining most of all these scales are going to be working. Not bad. So next, let's test a resistor. Let's see how well the Vedolyzer does reading resistance. So I'll move this from the DC volt scale to ohms. And what I need to do is, it says 0 ohms here, so I need to bring this needle right to the last line, just like the other VTVM that I just restored. So bring it right to the last line. So looking at it straight on, it's about right on the last line. This is just a rough test, so we'll see how this is doing. So I'll leave it on the same button. This is on the 20 volts DC button here, so I haven't moved that. And that is also the RX, which means resistance times 10 k ohms. So you can see it says 10M. Again, that's 10K. So 10K has how many zeros? It has 4 zeros. So we put 4 zeros after this 1 on the top scale, and we get 10K ohms. So what I'll do is I'll grab this 10K ohm resistor that I'm going to test, 2% tolerance. I'll put this on here so I don't have to touch anything, so I don't want to add to the resistance. And that should point right to that 1, right on that 1 line right there, if this is reading correctly. Look at that. This thing really doesn't need that much of an alignment, does it? It can be touched up just a little bit, but that's extremely close. So looking at it straight on, it's pretty much right on the 1. It's actually about a needle's width below the 1, which isn't too bad. So let's see with the other voltmeter again. Let's see if it's right on 10K or if it's maybe a little bit below. Maybe the Vedolyzer is actually correct. I'll just measure this. No, it's 10.1 k ohms. So it's very close. Very, very close. Again, could use a touch-up. But that's getting very, very picky. You know, we're talking a needle's width, you know, in order to have that read correctly. Amazing. So the ohm scale is working. So why don't we test out the wave meter? Let's see how that works. Let's see if the wave meter portion of the Vedolyzer works. So what a wave meter is really is just an early frequency counter. By tuning the wave meter, it'll allow you to identify where a frequency is. And I'll give you an example of that. So my signal generator is set to 450 kilohertz, so just below the standard IF of a normal receiver. And the output is set to 50 millivolts to give us a pretty strong signal, so it's easier for this thing to find right now. It's really sensitive. That's actually a really big signal for this thing. So I'll just plug this in here. So right now we're on band D, so that's D right here. So you can see the scale here. What I'll do is I'll just turn the brightness down for a moment. You can see on the scale here, it says 210. So I want to bring this, see 230 and then 240, I want to bring this up to 450 and watch what happens when I get close to 450. See how this is starting to raise up here? Now that's with no gain. So 50 millivolts is a lot of signal. So what I'll do is I'll just turn this up, say to about this point right here, and I'll get close to 450, and as you can see, I not only get a reading here, but you can see it's raising the level over here on the meter as well, so we can use both the CRT and the VTVM to indicate where a signal is. We can really use this to find where that peak is, and where the peak is, where the maximum is, we would read the scale, and then that would tell us that we're at 450. Now, this is off just a little bit because it needs an alignment, but it's very close to 450. So I'll just brighten this back up again. So if I want to tune the sweep in, well, it's pretty much right there. Look at that. And that's the signal. So you can see as I tune off frequency how it goes down. So we can either use this to peak up the wave meter, or we can use the VTVM to do it. Really nice feature. Both of them work at the same time. And there's quite a broad range of frequencies here. So that even the wave meter on this thing is working. Everything seems to be working. So the only thing I haven't tested out right now is the AC volts. And I'm pretty sure that works. Let's just give it a quick test. Let's test out the AC voltmeter portion of the VTVM. So I'll move the function selector switch over to AC volts over here. This row of switches is in the voltmeter off position. This button on the bottom is pushed in. So what I want to do right now is re-zero the meter. Bring that right up to the 0 line, like that. I have 7 volts AC on these two probes right here, so I want to select the scale that's going to read that the best, and that would be the second scale up. 9 volts, 8 volts, 7 volts right there. Right here is the 9 volt AC button. Press that in. So what do you think? Think it's going to read close to 7 volts? No alignment? Let's find out. Look at that. Right on 7 volts. Why am I not surprised? This Vedolyzer really is quite amazing. This thing has gone through such an incredible restoration and rebuild, and for this thing to hold its calibration so close throughout that entire procedure is really nothing short of amazing. So the designers at Supreme really did a good job on this thing. I'm really impressed with this. So now, all this thing really needs is a touch-up alignment to bring this thing right back onto spec so that we can use this thing to start servicing things. So if you're interested in that alignment procedure, let me know in the comments below, and if there's enough of you that are interested in that, I'll make a video on that and I'll take you through the entire alignment procedure of this Vedolyzer as well. I realized I didn't answer the trivia question in the previous video, so here it is. So 2 videos ago, I posed the question, what are these little devices? So if you want to guess what these things are, pause the video now because I'm about to tell you. So these are known as Fettrons or tubesters, and these things were a solid state replacement for vacuum tubes in a lot of pieces of test equipment and in some radios and things like that. So that's what they are. There's a little die inside, and basically it's just a solid state vacuum tube that plugs into the same socket. These things have been around for a long, long time. And again, they're known as Fetrons, or in some cases, tubesters. That's what those are. So now for the next trivia question. What is this device right here? Answer in the next video. Thanks for stopping by the lab today. I hope you enjoyed seeing the Vedolyzer come back to life. If you are enjoying my videos, you can let me know by giving me a big thumbs up and hang around. There'll be many more videos like this coming in the near future. We'll be taking a look at both vacuum tube and solid state electronic devices alike. So there'll be a lot of repairs, restorations, troubleshooting procedures, alignment procedures, and even some circuitry design on this channel. So if you haven't subscribed, now would be a good time to do that as well. If you want to be notified as soon as I post my new videos, don't forget to click the little bell symbol. I'd like to thank both Steve Johnson and the YouTube site Restore Old Radios for all the information that they've provided throughout this entire restoration procedure. I'll link both of them underneath the video's description in the Show More tab. So just below the video's description is a Show More tab. If you click on that Show More tab, it'll expose all the links. So I'll link Steve Johnson's site in there, and I'll also link Restore Old Radios. That's Don's YouTube channel here on YouTube. Definitely worth subscribing to. I've subscribed to Don's channel myself. I'll also link under the Show More tab, I'll link the previous 2 videos on the Vedolyzer, so you can click those if you haven't seen the 2 previous videos on the restoration for the Vedolyzer. If you're interested in learning how I reverse engineer electronics, and if you're interested in the technique and learning how to reverse engineer electronics yourself, you might want to check out my ongoing electronics course on Patreon. I'm also sharing many of my electronic designs and inventions there. All the plans, all the circuitry design, everything is all up there. And there's a lot of videos there too as well. So definitely check that out. I'll put that link under the Show More tab as well, and I'll also pin that link at the top of the comments section. So click on that and it'll take you right there. Until next time, take care. Bye for now.